Nobody ever told me that this course was theoretical, but okay, I'll take it. Let's continue with message-oriented communication. The first thing I want to talk about are transient messaging, transient messages, and their sockets. How many socket programmers are in this room? Oh, please, more? More. No? Very long time ago. I'm getting old. I think I mentioned this before. Sockets are most of the time they're the lowest you can get in messaging in distributed systems. And in many distributed systems, they are still very, very popular. There is this great book on network programming and Unix programming, actually, written by the late Stevens, I should say. He passed away years ago. These books are this thick, okay? And every sentence has content. And one of these books is entirely on socket programming. I have a reference in the distributed systems book. If you really want to get down into the details, that's the type of thing you need to get. Take a look at the book and you'll find a reference. Now, where do sockets come from? They were implemented in the early Unix systems, and I would say that because of the free distribution of the early Unix systems with the socket stuff, that's actually how distributed systems became popular, because the free was a very simple way to actually do network programming, and that's it. Now, this is the kind of socket interface that you would get. There's this data type called socket, and this is nothing else but a local data structure to keep an account of everything you want to do with network programming. And notably, for example, for a TCP connection, it maintains stuff about that TCP connection. You have a number of interesting calls. One of them is bind, which means that I can attach or associate a local IP address with a socket. On the client side, it's often automatically done. You have listen. Listen is kind of a strange thing. It's used in different contexts in different ways. But the listen statement is used on the server side to tell the operating system to reserve enough buffers so that the server can accommodate I think by default, at least 5 TCP connections. Okay? But the server could say, no, I want to have at least 10 or 20 TCP connections, which means that more buffers would be reserved. The accept statement is something that is called by the server to just sit and wait until a request comes in. And in fact, it's a request to connect to the server. We'll get to an example in just a minute. A connect is typically something that's called by the client and say, hey, server, I want to talk to you. Then you set up your TCP connection, after which you can do the send and receives. I will replace the send and receives with write and read statements. This has everything to do with the approach that many Unix systems take, is namely to present everything as a file. And there is no fundamental reason why you cannot represent the communication over a link as a file, because you're just writing stuff to a file and you're reading stuff from a file. And then finally you can close the connection. Okay. This is, if you find any piece of code for client-server computing, you will always, and of course there are exceptions to the rule, find this scheme. You have your server that will create a socket, bind a port and or IP address. Many servers have multiple IP addresses, but here you have this association with basically the endpoint that client should talk to. You tell the operating system how much buffer space it should reserve or how many connections it should accommodate, and it blocks here until it receives an accept. The client creates a socket and directly goes to the connect. And I'm suggesting here indeed that the bind on the client side is done under the hood. You can do this explicitly, but normally there's no reason to do so. You call the connect, and then at this point, the client and the server will synchronize. Synchronize is a dubious word. You know, it's used in different ways. Yes?
Just for my personal understanding, you set the port in which you communicate to and bind, right?
I'll show an example that's actually code, and I think it's on the next slide, and then we can go into some of the details. Okay? There is some nasty stuff going on. Nasty stuff, not nasty, but I think that will answer your question at least. Once the connection has been established, you can get into a read-write cycle. Okay, this is where the communication actually takes place. After which, and there are variations here, both close the connection, one closes the connection, it really doesn't matter. Okay? But what I'm trying to say is, if you take a look at client-server communication, you will virtually always see this pattern between the client and the server. It may be hidden very deep away into your code, but that's the pattern. This is how it works. Okay, let's make this concrete. This is, I would say, almost Python code. Actually, I did get it running, but I removed some statements just to fit it on one slide. But here you see how this could work. How many of you are familiar with Python? Very good. Years ago, somebody tried to convince me to use Python because it was such a great language. Yeah, sure. Years later, I started to use Python and thought, hey, this is really a great language. I think it's, well, it's becoming one of my favorites. When I program, I never hardly program anymore. I have this habit of taking Python. Okay. So watch this. Okay? Here's your server. And it has a host, really doesn't matter, there are some initialization things here. It takes a server port, this is the port that it will listen to for incoming connections. It imports the socket library to create a socket. And the only thing I'm saying over here is, hey, it should adhere to the Internet Protocol and it's going to be a stream. This is just a kind of a classification of that socket. And I bind my, let's call it IP address, and the port that I'm going to listen to that socket. Okay? And then I start listening to this thing. This N over here is by default 5, so accommodate 5 TCP streams. And here comes the part. I say, okay, I'll listen. I move on because this is something that you don't need to block on. This is where you block. So you call an accept, and this is where the server stops until it has an accepted connection. Okay, let's jump from here to this point over here, to the client. I'll come back to the server in just a minute. So the client side imports the socket. It says, I know where the host is. Okay, it gives this domain name, could have been an IP address, really doesn't matter. It knows the server port. Let's just assume. I wanted to say let's assume this is by magic, but I'll come back to that in just a minute. It's a well-known server port, for example. It creates a socket, again, following the Internet Protocol, and it calls connect. It calls connect to the combination of that host and that port. Okay? The server over there was blocking until it got a connection request, and it gets out of this accept. And now something interesting happens. It gets a new socket and the address of the client. And this new socket is, I think, where your question actually referred to. Okay, then we'll get back to your question in just a minute.
No, it's already answered. It's just when do you bind to the port?
Oh, when you bind to the port, you do this. When you bind to the port, certainly before you call anything like accept. Yeah. But notice that the client has no bind statement here. That's just then under the hood. And in this case, forever, what you do is you receive stuff over this connection. If there's no data, you jump out of the while loop and you send some data back. Okay? So actually the data that you receive, you send it back. And this just goes on and on and on, and finally you close the connection. And on the client side, what you do is you send hello world, why not? You get some data back, and then you close the connection. Okay. First question. Where do you get this information from? This one over here, and perhaps this one over here. Hmm? No. It's the registry. That could be an answer. It's a correct answer. One of possible correct answers. Could this be? So I think we all agree that server port here should be server port over there. This guy is running on a different machine than this guy over here. So let's come back to our RPC stuff. I hope it's not difficult for you to imagine that your stubs may be Python code. You can have an IDL compiler that generates Python code, right? And what you would then could do, I should say, is in your interface specification, you say, hey, it should be this port. And then what happens is that thing is just automatically generated for the code that you use for the client and the server. In this case, server port would be included in your header file. You could import the header file. Great. Okay, now you know what the server port is. Okay, so what does this code actually do? Echo. It's just an echo server. No more, no less. And it actually works. It's real code. Okay, so the interesting thing is, in just a few lines of code, Python code in this case, I've written a real client-server program. And what's also interesting, it has everything there. Okay? This is as simple as it gets. What's going on over here?
You wait for a connection.
Wait for a connection, you get a connection back. And then what?
You send and receive data as long as there's data sent
Uh-huh.
from the client to the server.
So who's talking to whom? You get a connection back. You get a socket back. What does that suggest? Yes?
That you can also wait to other requests from you?
Yes, indeed. You can wait for other requests. So in terms of devising a multi-threaded server, what you could also do at this point is you pick up the connection and you start a new thread that will then handle what is associated with that connection. Okay? That's all clear to everyone? So what happens under the hood? Yes?
Well, when the client connects, it creates a random port that
Yes.
uses to the connection. That's where the server talks back to.
That's exactly what I wanted to hear. So when you get back a new connection, what happens is that a new port is created or used for the subsequent communication with the client. So this dedicated server port is used to accept connection requests, but after you accepted a connection, you actually use a different port to handle the subsequent communication. It's not strictly necessary, but my God, is it convenient to do it that way, okay? And really, you don't want to do it differently. And you really have to realize that now the binding is implicit and under the hood, now also on the server side. So the client does get the information back, talk to this port, you talk to port 80, but now that we're talking, you talk to port whatever it is. Okay, because port 80 is reserved for accepting connections, but after that, hey, you're in a conversation with the server. And you see this more pronounced when you actually start a separate thread that is thread or process that is operating now completely independently from the main thread that was just accepting incoming connections. Does everybody see the pattern? Is this difficult? There's only one answer here. No. Thank you. Okay. Let's take a brief look at message-oriented middleware. Oh, by the way, I again promised today that I will stop on time. That's because guess what? I have another meeting. Message-oriented middleware. It is actually very, very simple. The interface is extremely simple. There are some variations on the theme, but the whole idea is that you have these queues and you just put stuff into queues, and then the middleware takes things out of queues and moves messages around and puts them in queues at a destination. And that means that you can actually have an interface like this. Put a message in a queue, get something from a queue, poll, let's see if something's in the queue, or notify, hey, there's something in the queue and I'm telling you right now. And that's it. That's simpler than the socket interface. So the only thing I'm skipping here a bit are some control things, but if you take a look at real message queuing systems, this is the type of interface they actually have. So that's kind of simple, right? So it has to be difficult somewhere. In just a minute, I will talk about an actual system, WebSphere systems. It used to be called MQ series, and then we'll see how this works in practice. Okay. Now, what you often also see in message-oriented middleware is that you have a broker. And a broker is a very important beast because what you do in many cases is you develop, you have legacy applications, legacy systems. Legacy means they've been out there for a gazillion years. Nobody wants to touch them because the developers are gone and nobody knows anything about the code except one thing: it runs. Okay? You don't want to touch those systems. Now, if you have these legacy systems that need to exchange data with other legacy systems, what you can do is you can tie every legacy system to every other legacy system. So if you have n legacy systems, then you will have to have approximately order n square combinations of, combining two legacy systems. That's kind of a painful exercise. So what people do with message-oriented middleware is they take a message broker, and the message broker has a job of accepting all messages from any legacy system, seeing what it needs to do with that, and actually moving those messages to those other legacy systems. And what this means is that you put all of the complexity into the message broker. Okay. So what does these message brokers do? Centralized components. They basically solve all the heterogeneity that you have with all your legacy systems. And in the essence, they often provide so-called subject-based routing. Okay, here's this thing. And let me see where I need to go nasty. I need to go nasty at this thing over here. Okay. And I'm going to be nasty, not to you, but I want to place warnings. Okay, and I will tell something that I always, I used to tell to managers who I was explaining middleware to say, okay, this is where you have to watch your money. Okay. So there are different ways of looking at message brokers. The simplest message broker is the one where you have your legacy systems. In technical terms, you may have a client and another client here. One is the source, one is the destination, but those two do not necessarily need to know about each other. The only thing that I do know at the lowest level is that this guy has data that is interesting for this guy, but the format of that data is not such that this guy can just accept it. So what you do is the following. Your source client is an application. To make this clear, it could be Word. Okay, really think about that. Word is a non-networked system. And let's assume that the stuff that you're producing in Word needs to be processed, I don't know, by a spelling checker over here. Okay, but that spelling checker is not a Word spelling checker. It's a fancy dictionary-based spelling checker running on a, let's say, a Linux system. Okay, and Word on a Linux system is not a very good combination. Word runs on Windows systems. And I'm not going to do any Microsoft bashing. I always do a bit of Microsoft bashing, but let me tell you the following. I try to move transparencies, these slides, to OpenOffice. Okay, and I was working in OpenOffice, and yes, I decided to stop that because PowerPoint is really much better. Microsoft, you should be grateful to me. Don't worry, there will be another point during this course that I will not say something nice about Microsoft, but I may remove that from the recordings. Anyway, you have your application over here, let's say Word, and you want Word to talk to this dictionary-based spelling checker. It doesn't have the data in the same format, so what you can imagine is that, here's a keyword, you build a wrapper around this application, and the output from Word is fed into this wrapper. Wrapper is a program, okay? It takes the output from your Word program, which may be just files, and puts that stuff into messages that it sends to the message broker. And the message broker knows where the spelling checker is, and the only thing it now needs to do is pick up messages from a queue, see what it needs to do with these Microsoft Word formatted files, transform that, and hand it over to, in this case, the queue that is associated with that spelling checker. Now, the crux of the matter is that the rules for transforming that file into something that the spelling checker can understand is here. Okay? So all the logic, so to say, is concentrated in one point. That is good. Okay? Because just imagine that there would be another spelling checker program or a grammar checking program, and that it would have, again, a different format than the spelling checker could take. Then there's no need to bother these guys over here to enhance them with yet another wrapper or anything like that. Just concentrate on the complexity at the broker program. That's the good thing about the brokers. Now, the thing I just mentioned, that's maybe a very simple rule. It may be transforming one binary format into another binary format, or a text format into another one. So if you take a look at the old Word documents, they were kind of binary-like. Microsoft Word now uses open formats, and a broker would typically do that kind of a transformation. They are simple. You don't even have to know what the content is all about. That's the most important observation. Stuff gets nasty. Yeah, sure.
Why not talking about marshalling here, we're talking about broker, for example? Because marshalling is also about transforming the data and so that the other side can...
I like this question a lot. So let me rephrase it a bit. What's the difference with marshalling? Okay? And because marshalling was really simple. You take one representation of an integer and you transform this into a string, for example. I like this question a lot. At this level, there is not that much difference. It may be a bit more complicated, but there's no fundamental difference in this case between marshalling and the conversion I just described. Okay? Now let's enhance this a bit. I am suggesting here that one way or another there is a kind of a tight coupling between the source and the destination, because things are being transformed because you want your file to be spell checked by that specific spelling checker. Now you can do this a bit differently. You can say, okay, let's introduce a loose coupling, and what you do is you, as a Word program, you feed your data into these queues and say, spell check. Okay? And now you have a tag to your file saying what you want to do with this. In that case, you can have a more sophisticated broker that says, okay, I got this stuff. Oh, spell check. I have a bunch of spelling checkers over here. There could be multiple. And they all say, hey, give me messages that have spell check in their tag because we know what to do with them. So now what the broker can do is match clients to potential destinations, and what I'm just describing to you is an implementation of a publish-subscribe system, a tag-based publish-subscribe system. Okay? You can easily imagine that you can come up with these things, other examples. Now this is a really interesting example because if you take a look at your realm of legacy systems, I have just established a decoupling in space of legacy systems. I put a broker in the middle that will actually establish that two parties who don't know about each other can actually work together. So the broker does the matching, and it makes sure that what it sends off to this other legacy system is in a format that this guy can understand. Okay. And this is now the point where I tell managers to watch their money. There are people who say, well, you know, we can make intelligence brokers. I hate the word intelligence. If I now talk to AI people, say, yeah, I know, we hate this word as well because, you know, intelligence is not the case, it's advanced. I hate intelligence because we're intelligent, but programs are stupid. It's just as simple as that. So what does an intelligent broker do? An intelligent broker does content-based matching, content-based routing. And what this means is that it looks at the content of the messages it gets and knows by magic, by intelligence, oh, it's all about X. Let me send it to this guy over there because I know exactly what X is all about. Okay? Well, that's nonsense. Intelligence is not in the broker. Intelligence has been programmed there, right? Well, you get the point. And then I tell these managers, and you got to pay these guys because they're experts. And that's where it hurts. So an intelligent broker is a message broker with lots of programs that can recognize content, know what to do with it, and it's most of the time at least half manually programmed. No intelligence, but extremely expensive and often very, very useful. Let there be no doubt about that. But for managers, this is where, you know, it's going to hurt. So, if you ever see the word intelligence in association with middleware or distributed systems, you get into alert mode. Okay? Because intelligence is often then used to hide really intricate stuff. If they talk about advanced, that will be okay, but you get into alert mode. And that's where you dig into this stuff. Okay? You cannot, from a distributed systems perspective, accept that something is intelligent. It's not. It means that just there's a lot of things going on under the hood that you need to figure out. When you got to my website, you know that there's this rule. I have this rule, this statement up there for a very long time. Intelligence, a device you do not understand is not by definition intelligent. And I really mean that. When we're talking about distributed systems, if you do not understand what's going on in a distributed system, please say that you do not understand what's going on. Don't call the distributed system intelligent. I'm okay. I'll stop here because I could go on and on and on. I'm trying to encourage you to look under the hood and see what's going on because you do have the intelligence to understand what's going on. Yes?
But would adding one extra active message get the same result as communicating functionality to the broker? So
Could you repeat that question?
If one tag is not enough to identify, to narrow the possible destination to the national group,
Yes.
why not add another message?
I'm not quite sure if I understand your question. No, I don't understand your question.
I mean, the intelligent brokers are supposed to find exactly which destination should correspond to the message. But why not add another tag to give the same result?
Okay. Now I see your point. So the claim now is that an intelligent broker has to find out where to hand off a message to. Why can't you program this directly? Is that your question? Yes. That's actually a good question. What I'm saying is that the difference between a broker that concentrates on a publish-subscribe system is that that broker just has to read tags. Okay? But there are brokers out there that do more. They actually analyze the content of a message and then decide what to do with that message. And let me try to make this a bit more concrete. Perhaps you can imagine that you can install all kinds of filters. No, whoops, one step back. what you may be able to imagine is that you can have a collection of brokers in a network, and that what you need to do is you need to route a message from broker to broker. And actually, I will come to that example in just a minute. You have to route a message from broker to broker, and you have alternative ways of routing a message. Yes? If you can analyze the content and apply filtering techniques, saying, well, if this message is all about topic X and Y, and by the way, it's about stocks, but not the ones that have values higher than $100, then send the message to that broker. And otherwise, send it to that broker over there, to another broker. That's content-based routing. And in a content-based broker, what you actually do is you don't tell the broker what the message is all about. I'm exaggerating a bit, but you let the broker find out what the message is all about and then take a decision on how to forward that message.
But why can you just tell?
And if you would then ask me, isn't it simpler to tell the broker what it should do? Then the answer would be yes, but not always. Because if you give me that example, then I would say, isn't it even simpler for the client to say, broker, get out of the loop, my message goes to that guy. And then you would say, okay, that is indeed simpler. What you would then do is tell Word, will you please convert it to the format of the destination? Yes. And if you want to have the grammar spelling, will you also have the code with you to transform it for that grammar speller? And that was exactly the situation we were trying to avoid.
So it's either making the wrappers around without creating more complicated on the brokers.
Yes. And then that's the key observation. And the general observation is to put the complexity in one place, namely with the brokers. Okay? Okay, let's move on to an example. IBM's WebSphere MQ. It used to be called MQ series. Same product, different name. Application-specific, this is the model. Application-specific messages are put into and removed from queues. Queues reside under the regime of a queue manager. And a very important issue is queues are conceptually always local to you. I'll get to this notion of locality in just a minute. So processors can put messages only in local queues, not in remote queues. So you put something over here, okay, and then the middleware will start processing this stuff and moving it through a whole system of brokers, actually. Okay, where do I have? I'll just go to this picture over here. It looks complicated, but in fact it's not. Not that complicated. I have a sending client, meaning I have an application, and an application has an interface to an MQ system, MQ, message queuing interface. This is a stub. This is exactly the same stub that I was talking about when I was talking about a remote procedure call. Okay? And this stub implements the put, the get, the poll, notify interface that I just mentioned when I was talking about message-oriented middleware. And it is a stub with its counterpart at a queue manager. And what the queue manager can do is take stuff and put that into local queues and hand it off to the network. Now, when I explain this to people from IBM, their first remark is, hey, you can link a queue manager to that program. There's no need to have separate machines. Kind of obvious, right? I did this on purpose because this is exactly how MQ series supports this, and this is what I just meant by over here, local queues, or through a simple remote procedure call mechanism. So the RPCs in the MQ series are used strictly for something that is really close by. And the closest you can get is linking it to your application. It could also be that the queue manager is nothing else but another process running on your machine, and then you can still use an RPC mechanism. Why not? RPCs can also be used on the same machine. Everything goes through the operating system. But if you want to do this practically, the queue manager may be a dedicated machine on your local area network. And the assumption here is the communication has to be fast. So if the queue is on your local area network, it means it's still a local queue. That's the idea. Okay? Now, what's important in these queue managers is they have these routing tables. And you got to realize that before I actually came up with this picture, years ago I plowed through about 1,700 pages of manuals of MQ series. It always amazes me how thick documentation can be. And my terminology is inconsistent with what is happening in what was described in these documents, but it's better. Because, why is it better? Because they were using terms, I'll be specific, aliases in two completely different ways that was so confusing to me that I thought, it's not about aliases. I will use the word alias in just a minute. So I made that difference. And then they don't talk about routing tables, but they are routing tables. And I don't know, I can't recall what they are referred to in the IBM terminology. But when I explained this to people from IBM, they said, oh, that's the way it works. At least some of them. The routing tables, what they do is they take a message. They know, very important, they know how you can have a network of queue managers. So if you provide information on where a message should go to, they look into their routing table and say, messages with this destination should be put into this local queue. And then your message will be routed through a series of queue managers. These routing tables are there and they give you this information. Okay? So a message that comes from this guy over here is picked up by the server stub. The code looks into the routing table and puts it into an appropriate queue. Then you have these message channel agents, and these message channel agents are nothing else but interfaces to TCP connections. Okay, so a message channel agent sets up a TCP connection to another message channel agent, and then, hey, you can have your messages flow. And then you can go from queue to queue to queue. Small queuing systems had one of these queue managers, or maybe two. But I've been told that there are examples of really big message queuing systems with up to, let's say, 100 of these queue managers. And the queue managers jointly form an overlay network. Is that clear to everyone? They can be running on the internet, but they form an overlay network because from the logic perspective, it's only the queue managers that really count and that talk to each other. Okay. And here's an example. And I always forget which. I want a message to flow from here to there, but not directly. Okay, and I always forgot which one. And I'm not going to figure out here. So here you have let's just take an example. Here I have an alias table, and you have to realize that I have an application, and that application can, for example, use the name LA1. This is a local name. It's a local alias for a destination. So you write your application, and you say, hi, send this message to LA1. What happens is that when you talk to this queue manager, it looks up in this table what LA1 stands for, and it really stands for queue manager C. So then it looks up in its routing table which local queue it should use to forward messages to QMC. In this case, it would be SQ1. So it will put that message that came from the application that was labeled LA1 into this queue. That will go through your network. It will arrive over here. And then it will be tagged with this QMC, will be looked up into this routing table, and it will be put into this queue. Okay? And then finally, it would indeed be received by this queue manager. Now watch this. This is a local tag. So LA1 over here has a different meaning than LA1 over here. LA1 is a local name. The queue managers are global names.
This
Yeah.
means that the QMB always forwards messages from QMA to QMC. There, he doesn't look at the message itself, just where it comes from.
Yes. Yes, if I recall. So I have to repeat your question. When a message comes in at QMB, will it look at the local label LA1? No. It will.
It just looks at the sender and will pass it on no matter what's in the message.
Yes, it will just look at the sender and pass it on, and the destination.
Okay.
Okay, the destination was QMC in this case, and we'll look into its routing table what to do with messages addressed to QMC. Who fills these routing tables? The manager. No, it's the manager. The manager is a human being. And when you explain this stuff, people instantly say, also from IBM, oh yes, and it can be such a pain. So these tables are maintained manually. And that is actually the hardest part in maintaining a large message queuing system. Can it be done automatically? Yes, of course. But as far as I know, at least until a couple of years back, this was only partially automated, but there was still a lot of maintenance work to be done. And the maintenance concentrated on the routing tables. Yes?
Well, I researched QCSB. I don't know if you know it.
No.
It's also a message queuing system
Okay.
based on Apache.
Yes?
And there
Oh,
are,
yes, okay, yeah.
Apache
Yep.
ActiveMQ. And there are possibilities in discovering other brokers or message queuer to create your so-called routing table.
Yeah.
It's possible, but it's really, well, there are some hooks and eyes in it before you get it to work good.
To repeat what your remark, if you take a look at other systems, and there's one running on top of Apache, there are tools to actually fill in these routing tables. What you mentioned was something very important. In order to fill routing tables, you have to have a discovery protocol. Okay? You have this discovery protocol in the internet. That's obvious on very different ways. You know, if you do the Dijkstra, what you do is you collect information from all your routers, and then every router will actually compute an optimal tree. If you take a look at BGP, it uses, in essence, the Bellman-Ford algorithm to discover paths. But there's still a lot of manual work to be done. It can be done, but it is, at least for me, it's surprising to see how little has been done when it comes to automatic configuration of routing tables. Yes?
But what happens if a broker crashes?
What would happen if a broker crashes? This is the last question for today.
Well, all messages get stuck in the queue and will be delivered when the broker is back up.
Yep. That's one kind of obvious solution. Broker crashes. Let's hope it didn't lose too many messages, or that those messages that it had were backed up or available at other brokers. Okay? And then when that broker comes up again, hey, the flow starts. Now, think about this. Can you afford this in a message queuing system? Give me the answer next week. And you know the answer. Okay? I'll see you guys on Tuesday.